So let's continue with the lecture. Okay, in this video I'm going to do the lecture, and the next one I'm going to do the tutorial. Okay, so here we are still in section in part 4. Okay, matrix operations. Matrix operations. Okay, but this time is section D. Part 4, section D, where we will be discussing inverses. Inverses. Okay, so let me start with the definition. Okay, matrix G is a left inverse matrix of the matrix H if GH is the identity matrix. Okay, so matrix G is left left inverse matrix of the matrix H if GH, okay, maybe let me be a little bit fancy here, if G, okay, G in green is the left, okay, matrix, or the left inverse matrix. Okay, so if GH is the identity matrix, is the identity matrix. Okay. We have a two three element to view in this definition. So, I mean, you can guess it is the right version. Okay, it is the right inverse if HG is the identity this time. Okay, so it is right inverse if HG, okay, this time is G is on the right hand side, if HG is the identity. Okay, the last element here is a matrix H, a matrix H with a two-sided inverse is an invertible matrix. An invertible matrix. Okay, and that matrix is often called, you know, H minus 1 or H inverse. Okay, that two-sided inverse is denoted H minus 1, H inverse. Okay, and I am sure through some words we have used so far, you can you can see where we are going. You know, we are going to do to see some links between inverses and the non-singular matrices. And if we are talking about non-singular matrices, we are talking about which type of maps we are talking about isomorphisms. Okay, so I'm sure so far you can see how everything is connected together, how from the map or the from the map we get to the matrices, okay, and how these new concepts we are seeing are all connected, okay. Isn't that beautiful? Linear algebra. I love linear algebra. I don't know why. I hope you too. Let's continue with the lemma. Okay. If a matrix has both a left, inverse, and a right inverse, then the two are equal. Okay, this is a very straightforward lemma to prove, but I won't spend too much time in the proofs of the theorems, lemmas, corollaries. No, I will just give them, but if needed, you can email me and I can provide formal proofs. Theorem. Okay. A matrix, oh yeah, this one I love it. A matrix, and it makes sense, of course. A matrix is invertible if and only if it is non-singular. That means a matrix is invertible if and only if it is a square matrix. First of all, it has to be a square matrix and it is non-singular. Okay, non-singular matrix is square matrix, but all the non-singular matrices are square matrices, but not all the square matrices are non-singular. Okay, I hope you know why, because you can be given a square matrix and after Gauss-Jordan elimination, you can have 0 rows afterward. So at the beginning, the matrix is a square, but it has some linear, some row combination. So we know that Gauss-Jordan or Gauss method allows us to remove any any linear combination among rows. So after we perform Gauss-Jordan, if we end up with some 0 rows, that means we are not dealing with the non-singular matrices. Actually, they are singular matrices. Even though the original matrix is a square, it doesn't mean that it is necessarily non-singular. Is that okay? So I'm sure you are able to make those subtle differences. Okay. So let's continue. Number 4. We have another lemma. Okay. A product. Let me change color. A product of invertible matrices is also invertible. Okay, it's invertible. And if we are talking about product of matrices, what is the underlying map? Do you remember? The underlying map is map composition. Is that okay? So let me continue with the formal expressions if G and H are invertible and GH is defined, then GH is invertible. And yeah, I'm going to change color here because this is you know, an expression or an equation to remember okay easily. So GH, the inverse of GH, okay, is not G inverse times H inverse, but we have to change, we have to inverse the order of the matrices. We have H, here we have GH, but the inverse will give us H, G, and their inverses, okay? H inverse times G inverse. Okay, so let me continue here with the let me see, let's see application of inverses. Why do we have to find inverses to begin with? Okay, there are reasons. Let me give you just two. Okay, inverses, application of inverses. Okay, so the first one is solving a linear system. Okay, so let's say we have okay, let me give you the reasons first, then I can give an example. Okay, the first reason why is we need to find inverses is the fact that having okay having the inverses or the inverse of the matrix speeds up the fact of solving the linear system. Okay, system, okay, with the same coefficient but a different constant. I will show you shortly. Same coefficients but different constant. Okay, so let me give you one example here, and maybe let me change color. Let me give you, let's say we have this the following equation to solve. Okay, 1 2 3 4 multiplied by x1 x2, okay, equals to 1 minus 2. Okay, if we know the inverse, okay, if we know the inverse of that matrix, okay, I'm going to give you the inverse. Okay, we can just say that x, the solution x1 y1, sorry, x1 x2 x2 is going to be equal to what? The inverse of the matrix, okay, minus 2 1 3 over 2 minus a half times 1 minus 2. I'm sure you know what I have done here, right? Okay, let me explain it to you. Let's call this matrix H times uh, let me write x1 x2 equals and equals 1 minus 2. To be able to solve that equation there, if I can, okay, so we will assume that h is non-singular, so it is invertible, it has an inverse, okay, two-sided inverse. So if I multiply the h by h minus 1, I'm going to multiply the right-hand side as with h minus 1 as well. So this becomes what? An identity, okay? Therefore, I am left on the left-hand side with the x1, x2 equals the H inverse times 1 minus 2. You see? Okay, so let's say we are given another equation, basically roughly the same with the same matrix but a different coefficient here. If I know the inverse, let's say we are given new coefficient. Okay, so we have the new equation is 1, 2, 3, 4, x1, x2 equals this time let's say I have 3, 5. Yeah, 3, 4. Let me use 3, 4 here. Okay, instead of performing Gauss method again here or Gauss-Jordan here as well, what if I can just multiply the coefficient here with the inverse of the matrix? So this time our new answer x1, x2 is going to be equal to the inverse that I have already calculated multiplied by 3, 4. Okay, so having the matrix speeds up the computations when we have the same matrix but with different coefficients. Okay, that's one reason why. And another reason is that having the inverses allows us to do what is called sensitivity analysis. Okay, having inverses allows the study of the systems sensitivity analysis. Okay, so basically the sensitivity analysis is what happens, what is the result when the coefficients are changed a little bit. What is the result? Okay, let's say here we have okay, for the first example here the coefficients are 1 minus 2. Let's assume that and we have the answer for the solution for the equation, okay, which is x1, x2. Let's assume that this time we have the new coefficient 1.1 minus 2. What is the new solution and how uh, and what is the difference in that solution, in those two solutions? The first one when the coefficients were, sorry, when the constants, not coefficient. Here we are talking about constants on the right hand side. They are constants, but the matrix is made of the coefficients. Just so, that's subtle difference, and I'm sure you can guess it yourself. Okay, so what happens when the constants are changed a little bit? What is the change in their solutions? Is that okay? So I'm going to continue on next page. Okay, okay, let me continue with yeah, number 6. Look at this lemma. Okay, a matrix H is invertible if and only if it can be written as the product of elementary reduction matrices. So here we can compute the inverse by applying to the identity matrix the same row steps, in the same order. I'm going to explain this to you shortly. In the same order, okay, that Gauss Jordan reduces H. Okay, I know this is a very long definition, but basically what it means is, if you remember from the previous video, we have seen how to get how we can have a reduced echelon form of a matrix by multiplying it by elementary reduction operations, or a matrices, elementary reduction matrices. So basically from the last tutorial, last video, we have our matrix H. We multiply it by R1, which are the reduction matrices R2, R3, dot, 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 R, R, minus 1, R, R. Okay. And when we did that multiplication, we got the identity matrix, the reduced echelon form. But this time we are talking about a non-singular matrices. Therefore, we are going to get identity at the end. Okay, so let me use identity matrix. Okay, so that what we can do is the inverse. That means the inverse of H is this product. This is H inverse. Okay, so if we can do what we have done in the tutorial, last tutorial, if we can find these reduction matrices, okay, and we multiply them together, we can get H that way. We can get the inverse of a matrix that way. But what if, we can do the same thing, right? So what if we can have our matrix H here and the right identity matrix there, and perform these same operations here. If we can perform those operations through this new augmented matrix, at the end we are going to get the H here and something here. Let me call it the H inverse. Is that okay? If we apply the R's here, the R1, R minus 1, dot, 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 oh sorry, R, until R1. If we do the same steps to this augmented matrix, then we will end up with this new matrix. So basically that's what the lemma is saying. So basically lemma is telling us how to find an inverse of a matrix the easiest way. So just write the augmented matrix. You write the main matrix on the left hand side, and write the identity matrix on the right hand side, and you perform Gauss-Jordan method. Is that okay? So the answer you have on the right hand side is going to be the inverse. I'm going to do it in the next video. I'm going to do the tutorial in the next video. But here, let me give you another corollary, and then we will stop here. We will stop the lecture here. So number 7, corollary. Okay. And I'm sure you know the inverse of a 2x2 matrix. So here, the inverse for a 2x2 matrix exists and equals So if you have the matrix A, B, C, D, okay, its inverse equals 1 over AD minus BC, D minus B minus C. So basically we have 1, I'm sure you know this formula, 1 over, we AD, multiply this diagonal minus this, the other diagonal, if I can call it that way. And then here, this matrix here, we just, for the first diagonal from left to right, let me say that way, we just swap places, and for the second diagonal from left to, from the bottom left to the top right, we just change signs. Okay, so this is a good formula to remember. If, okay, there is a condition, the denominator must be different than 0, and that should let you think of something. What that thing is going to be discussed in the next chapter. Let me write it first. If and only if AD minus BC is different from 0. Okay, what does this thing often called? The determinant. Okay, so we are going to discuss determinants in the next chapter. And from this chapter, or from this corollary, you can see the importance of determinants. The determinant helps us to determine something. To determine what? To determine if the matrix has an inverse or not. And that means the determinant allows us to see if the matrix is singular or non-singular. Isn't that beautiful? I know. Okay, so I'm going to stop here, and in the next video we will do the tutorial how to find the inverse of a matrix. Okay, see you.